So it's my pleasure to introduce Sinan Müftü to the platform. He's the Associate Professor at Northeastern University, Department of Mechanical and Industrial Engineering. He's been working with Bicon for 4 years on various projects related to design considerations of different implant abutment connections and stress distributions on bone of different design implants. He has articles published frequently in respected engineering and biomechanical engineering journals. Dr. Müftü, thank you.
Good morning, ladies and gentlemen. I would first like to thank the symposium organizers for giving me the opportunity to present our research results. It's indeed a great pleasure and an honor to talk in front of you this morning. I'm going to talk about, in general, finite element analysis of various implant designs, and I'm going to also touch the results that we found for the 5 by 6 millimeter implant. So, however, I also would like to overview the recent research that our group has conducted in biomechanics of bone-dental implant interactions. I would like to acknowledge my students, Dinçer Bozkaya, Can Jagadnik, and Shanyu Chu, who contributed greatly to this research, and of course, the support provided by Bicon Dental Implants. And of course, my daughter and son, who has allowed daddy to do some work during this work. Dr. Morgan yesterday asked me if I had any skiing or fishing pictures. I said no, but this is a picture that we have taken in our last vacation in Turkey, so I thought I would just replace that here. With that in mind, I just want to review in one single slide the overview of our work that we have done in dental implant area. The first thing is we worked on mechanics of the implant abutment attachment methods for dental implants. I'm going to talk about that, and also the topic of today's presentation, evaluation of bone loading characteristics of various dental implant systems. So when it comes to mechanics of the abutment implant attachment methods, we looked at the tapered interference fit, or the so-called Morse taper. We developed some simple formulas to determine the various, believe it or not, these are very simple formulas compared to performing finite element analyses and trying to decipher the results of the finite element analysis. So with formulas such as this, one can easily determine the relations between practical parameters such as insertion depth and loosening torque. And of course some other things that I don't want to go into detail right now. In addition to tapered interference fit, we looked at the what I term as taper integrated screwed-in abutment attachment methods used by other implant systems. And again, there are some formulas that were developed, and again, we can determine parameters like the effect of tightening torque on loosening torque and parameters of that nature. However, that's all I want to tell you about this attachment method business. And the next topic, of course, is the topic of today, biomechanical evaluation of bone loading characteristics of dental implant systems. Now, when we look at this topic, why do we want to study the finite element analysis of bone loading characteristics? Of course, the answer is twofold. One of them is to feedback to the implant designers and manufacturers about the bone loading characteristics, whether they load the bone enough or not enough or too much. And the other one is, of course, to help give feedback to basic scientists who work in bone mechanics area. So analyses like this provide that possibility. With that, I'm going to be talking a lot of mechanical and engineering jargon today, and I'm sure you all know these concepts, but I just would like to review briefly mechanical properties of the bone. I'm going to introduce what stress is, strain is, and elastic modulus is, so that we are all on the same page. Once that's done, I'm going to talk about biomechanical evaluation of dental implants. I'm going to do this in 3 different flavors. Now, the first thing I'm going to do is I'm going to compare 5 different implant systems. Next thing, I'm going to look at the biomechanical evaluation of the 5x6 Bicon implant. And then I'm going to look at the evaluation of some implant groove types. Now, when I'm doing this, I'm going to increase the complexity of the biomechanical evaluations. First of all, I'm just going to use a criteria of bone overload to compare 5 implants. This is a fairly straightforward way of looking at things. Next, I'm going to look at the Bicon implant from a Mechanostat point of view, and when we come to it, I'll explain what that means. And then, when we are evaluating different implant grooves, I'm going to talk about bone remodeling. So, as you know, when during mastication, complex stress distributions can occur in the bone, and the stress is a pointwise quantity, so the stress would change from point to point to point. And a stress at a point can be represented by 6 different stress components. So, but when we look at these, we will see that mainly these are normal stresses and shear stresses. We'll talk about them. And they cause normal strains and shear strains. We are then going to talk about the definitions of elastic and shear moduli, and then we'll talk about the multiaxial stress just a little bit. So normal stress, typically, it's very easy to visualize it in the tensile testing. For example, if we were to test an aluminum piece or even maybe a piece of bone, we would prepare a sample, cylindrical sample, put it into a tensile tester, and we would impose an elongation and measure the force. And in engineering, it turns out that force and elongation are not scalable to generic laws, but stress and strain are scalable to generic laws. So when we plot the results of such a test, on the vertical axis, we get the normal stress. On the horizontal axis, we get the normal strain. And the proportionality constant for this normal stress, normal strain relation is known as the elastic modulus. Now, when we look at the shear stress, again, shear stress develops when 2 surfaces, which, for example, were glued over here in this footprint area, were made to slide with respect to each other, and a shear force develops, a resultant shear force develops over here, and shear stress is defined as the ratio of the shear force to the cross-sectional area. And this is an average quantity, of course, for this definition. And shear strain causes some angular changes with respect to a rectangular configuration, and shear stress, shear strain curve would look something like this. And so if things were very simple, we would have a very simple uniaxial tension test, and stress would be related to, normal stress would be related to normal strain with Hooke's law, and shear stress would be related to shear strain through a shear modulus. Now, before going into more complicated methods, let me just show you some pictures about the internal structure of the bone. As everybody knows, inside the bone is typically cancellous bone, and outside cortex is the cortical bone with a higher density. And a typical elongation test for cancellous bone looks like this, where over here we have the ultimate stress, but we really want to load the bone in here in this regime somewhere. As I said, due to mastication, a complex stress distribution occurs in the bone, and there are 6 stress components and correspondingly 6 strain components that develop in general, and they are connected through a generalized Hooke's law where this C is a compliance matrix. Now, in reality, bone is an orthotropic material, so we actually get 9 different independent parameters to represent the stress-strain behavior. But often, as was done in our finite element analysis, the bone is assumed to be isotropic. In that case, we can get away with 2 independent parameters. In that case, for the bone, for the cortical bone, the elastic modulus is typically 13 gigapascals. For the trabecular bone, it's 1 gigapascal. And the Poisson's ratio is 0.3. Now, there is ample experimental and theoretical evidence that shows that there is a relationship between the density of the bone and the elastic modulus. And when I say elastic modulus, I'm talking about the mean elastic modulus that we see at the macro level. So this relationship is in this general form where mean elastic modulus is proportional to a constant times the density of the bone to the power n. Now for cancellous bone, this power is almost 2, and for cortical bone, it's about 3. Now on to the topic of the day. I'm going to talk about biomechanical evaluation of dental implants, and the first we will talk about comparison of 5 dental implant systems, and the comparison criteria is going to be bone overload. So the implant systems that we are considering are these 5 listed over here, and the dimensions and the implant surface area in the bone are as given. Now, the comparison criteria is the maximum stress criteria, and it just, as I said at the beginning, it's a simple criteria. We are just looking at the bone failure, whether bone failure occurs or not. So to do that, we need to determine the maximum stress that occurs in the bone due to the loading and compare that to the ultimate stress that the bone can take. Now, it turns out that experimental measurements show that the ultimate tensile stress in the cortical bone is 170 megapascals in tension, but 100 megapascals in compression. And in cancellous bone, this is in the range of 2 to 5 megapascals. Now, again, just a little bit of more engineering jargon, but it's necessary. As I said, principal stresses or the maximum stresses are necessary to calculate, to make this failure criteria. So the maximum stresses that occur in the bone are the principal stresses, and they are found by solving this cubic equation, and the constants that occur, I1, I2, I3, that occur for this cubic equation are actually the stresses that are given by the finite element method. So when this cubic equation is found, it gives 3 roots. When solved, it gives 3 roots. The first one is the first principal stress, second principal stress, third principal stress. And in general, you would get a tensile behavior here and a compressive behavior here. It's not necessary, but in these analyses, that's what ends up happening. So we just check these conditions. So this is a summary slide. These are the systems that we considered. And what we are looking at is just the area at the intersection of the implant and the cortical bone in these 5 graphs over here. The load that we applied was an occlusal load at an oblique angle, applied a little bit off-center to the implant for all the cases, and we varied the magnitude of this load. Now, the good news is, for moderate levels of mastication loads, there are no differences and no failure occurs in any of these implants. But when we go to very high loads, which can occur in patients which have grinding problems, or in catastrophic situations when somebody tries to eat something that they're not supposed to eat too hard or something like that, the loads can go up to 1,000. I've read numbers of 2,000 newtons on individual implants or teeth. So when that happens, some differentiation starts to happen between the implant systems. The results are here, and I think we have a poster, so I'll be happy to talk about the specifics of the results. But since we are here for Bicon, I think Bicon fares fairly well in these so-called catastrophic situations. Now, actually, let's go back here. I'm just going to say something. Now, for a very high occlusal load of 1,632 newtons, it's 162 kilograms roughly. We find that this system, Ankylos and Bicon, have a failure area marked by this little off-mark color, and that failure happens due to tension. So this area is in tension, this area is in tension. So are these. The other implant systems, in addition to that, have failure at the top region. So if you look at why the Ankylos implant and Bicon don't have failure due to compression in this region, we'll immediately notice that this sloping shoulder business. So yesterday, Tom Driscoll explained very well why there are advantages to using the sloping shoulder, and I thought I would just present a back of the envelope calculation, an explanation of what that is. So if we turn the envelope and we look at the statics equilibrium of what might be happening in this interface, so this is the sloping shoulder of a Bicon implant, and this is the occlusal load coming down. And I'm making a gross assumption over here. I'm saying that all the load coming due to this force is perhaps shared only in the cortical region, and it causes this normal force and the shear force. So when we look at the forces, these depend on the external force by these cosine and sine relationships, and when we calculate the maximum stresses that are really generated by this, without going into too much details, if we look at the shoulder angle in the horizontal axis and the maximum normal stress that's developed on the surface, we see that actually right around, over here, the maximum stresses are reduced considerably. So that may be an explanation why the sloping shoulder system works quite well. And that's what Mr. Driscoll was explaining so nicely yesterday. So I think I talked enough about this. Let me go to the next topic. I'm going to next talk about, again, another biomechanical evaluation. So I'm going to increase the level of complexity just a little bit from a biomechanics standpoint. I'm going to change from bone overload criteria to what's known as Mechanostat, and I'm going to explain what that is. And we are going to look at the effect of this in the 5x6 millimeter Bicon implant. So this Mechanostat theory is introduced by Dr. Frost. And as you know, bone remodeling produces and maintains bone that is biomechanically and metabolically competent. And bone tissue adapts to mechanical usage. And the Mechanostat hypothesis of Dr. Frost states that the bone remodeling response depends on the strain level it experiences. Now, what are the effects of different strain levels? This is a diagram, a 90-degree version, 90-degree twisted version of this was presented by Dr. Lemons yesterday. So this hypothesis essentially says that if the local strains are below 200 microstrain, this will cause this will trigger a response which will eventually cause net bone loss. So this is this region, and we will have net bone loss. This is the strain, this is the bone mass. If the strains that the bone encounters are in the mid-range, that is 200 to 1500 microstrain, this will evoke no response. This region is also known as the lazy region, sometimes, lazy bone. So nothing happens, bone mass is conserved. And strains in the range of 1500 to 3000 microstrain will cause net increase in bone mass. So 1500 to 3000 actually is probably something that we would like an implant to impose on the bone. And if we go beyond 3000 or 4000, some catastrophic events start to happen. So we really don't want to move beyond 4000 microstrain. Now, I'm going to analyze the implant by using finite element method, but what type of assumptions do I need to make in terms of the bone quality and implantation depth and so on and so forth? So over here I have some slides, and in practice it's very obvious that the bone quality and insertion depth are patient and site specific, and you know this much better than me, of course. In certain cases, the implant can be inserted all the way down into the bone and with very fine growth of bone around it. And in certain cases, this looks like cortical bone, very good cortical bone coverage. Whereas in certain cases, there may be some non-integrated components over here, such as these, although all of these look pretty good. So in order to consider all the possibilities, this is what I did. We looked at, first of all, cortical bone thickness of 1 and 2 millimeters. We looked at different implant insertion depths, which I'm going to explain next. And we looked at extent of the cortical bone, how much cortical bone exists at the apical region of the bone. So this gives a total of 32 combinations. So we looked at all different combinations. For example, in terms of insertion depth, we looked at 4 different scenarios, as seen over here. And Dr. Grippo yesterday actually was talking about what happens if the implant, for some reason, gets exposed like this. It's not a desirable situation, but what happens? And, different bone depths. And we also looked at the thickness of the cortical bone, 1 millimeters or 2 millimeters, although 2 millimeter, I realize, is a very thick bone to be found in the apical region. And we also looked at the amount of cortical bone coverage. Now, let me explain what I mean by this. So this purple shell over here is the cortical bone. And in this region, when I say full coverage, there is full cortical bone. When I say 2/3 coverage, the faraway regions, 2/3 of the faraway regions is covered by cortical bone, but right around the implant there is cancellous bone. 1/3 coverage has more cancellous bone, and no coverage has no cancellous bone. So we looked at all those 32 cases, but we are only going to present to you just a few of them, just to give you a flavor, but the results are pretty much similar. So over here, we are looking at the results of the 5x6 Bicon implant, the so-called Fat Boy. And so we are looking at the effect of insertion depth for 2/3 cortical bone coverage. So around the implant, actually, we assumed that the bone is cancellous up to that region. So as we put the implant, or the implant is implanted deeper and deeper, the events that take shape place are as follows. When the sloping shoulder starts to engage the bone, we start to see a reduction in strains. However, before I say that, let's just look at the strain levels. So the strain levels generated in all of these cases, this case, and this case, are actually, and in fact also this case, are in the, when we look at when we look at the problem from a mechanostat point of view, are in the range where we would actually have bone growth. So this design creates favorable strain situation in the bone for all of the cases. Most of the strains we found are around the tips of the fins or the plateaus. And as we implant deeper and deeper into the cancellous bone, the levels of strains drop. However, they either still remain in the bone growth region or in the lazy zone. So we don't go down to less than 200 microstrain region. So in all of these cases, there is healthy expectations of healthy bone situation. Now, when I look at the effect of cortical coverage on stress distribution for a submerged implant, so all of these are submerged, but we are looking at the effect of cortical coverage. Now, this is fully cortical bone. What happens in this case is the stresses are highest in the cortical bone. This is a known result. Cortical bone has a higher elastic modulus and carries most of the load. When we have 2/3 coverage, cortical bone ends here. There is cancellous bone here, and the sloping shoulder in this particular case is creating the strain levels, the stress levels over here. In the next slide, I'm going to show the stress levels, and you will see that they are pretty good. And as we go down, as we go to different coverage, we see that the response really doesn't change. So this figure, and this figure are pretty much the same. So that means the cancellous bone, the coverage level of it really doesn't matter that much as long as there is cancellous bone. But if we can develop cortical bone here, then that makes a difference. Now, again, coming back to the strain, which is the Mechanostat approach, we see that, as I was saying before, if in the case of cancellous bone developing over here, the strain levels are in the bone growth range, so we would probably have development of strong bone development activity in this range. So in summary of this part, the strains for the 5x6 Bicon implant were found to be in the healthy range. The peak strains in the cancellous bone are reduced as the implant is placed deeper in the bone. The peak strains in the cancellous bone increase in case there is less cortical bone coverage. For totally submerged case, the sloping shoulder of the implant resists the loading, provided that the osseointegration took place. So with that, again, I'm going to increase the complexity of the analysis one more notch. And we are going to look at the bone remodeling. Now, the Mechanostat theory by Frost tells us that we expect that bone resorption or growth or no change in bone to occur as a function of strain in the bone. But it does not tell us how it will grow and what densities it will take. So the bone remodeling models, mechanical or mathematical, there are mathematical models of bone remodeling that tell us that. So I'm going to talk about that a little bit next. In his famous observations, Julius Wolff observed that every change in the function of bone is followed by certain definite changes in internal architecture and external conformation in accordance with mathematical laws. Now, modern theory does not like Wolff very much anymore, but this doesn't mean that there is no mechanical effects. The observations that are said that Wolff made was a comparison between a bone and a crane shaft. And he noticed, it was pointed out to him that the principal stress directions in a structure that looks like this are very similar to the cancellous bone orientation. So, in fact, this is a cancellous bone. So, based on observations like this, not only this one, but a long years of observations, he stated his Wolff's law. Now, modern explanation of this divides this bone remodeling into two major sections. Surface remodeling is thought to change the thickness and or location of the cortical bone. So this layer either grows or its thickness changes. On the other hand, internal remodeling changes the density and the orientation of the cancellous bone. And there are new theories relatively new theories, related to wound healing and tissue differentiation. And these can not only talk about these two, but also predict the generation of different types of tissues. So we are going to talk about the internal remodeling. I think I'm going to skip this in view of time, and I'm going to come here a little bit more mathematics. We use the model of Winans, Huskies, and Grothenberg. There are many other models. This is the one that we chose. You will recall that elastic modulus depends on the bone density. Now, this model tracks the changes of the bone density as a function of time, and it uses a property in mechanics known as strain energy density. So if the strain energy density is greater than a certain limit, it predicts a positive rate for density increase. If it's in the lazy zone, the strain energy density in the lazy zone, the bone density doesn't change. And as you can imagine, if it's lower than a threshold, it predicts a negative rate of change. And once we can find the density, we can calculate the elastic modulus. And this is all thrown into a complicated finite element program. I'm not going to go into the details of that. But first, I'm going to look at the results of this type of bone regeneration models around a V-shaped groove that you may find in a situation like this. So the model starts with, this is the titanium part. This is a V-shaped groove. It starts with cancellous bone all around it. It's loaded radially and axially. So this is the radial direction, this is the axial direction. And for simplicity, we only so far have looked only in one groove. So for the low loading case, the model predicts that some cancellous bone structure happens. For example, the radial load in this case is 4 megapascals and the axial load is 1 megapascal. And you see that the darker colors are the different higher elastic moduli, and the lower, the red and orange colors like that are the higher elastic moduli, and the blues are the lower elastic moduli. And the bone finds an equilibrium state where it can find equilibrium, stay steady, and develop this. So what happened is it was not loaded perhaps well, and it developed this bone structure. When we increase the load to 12 megapascals radially and 3 megapascals axially, actually we get much more cortical bone generation and some cancellous bone. However, we also see that this bullet shape starts to take place. In mechanics, it's known that arch shapes carry load very well, and actually nature, at least these equations, seem to find that. And if we increase it even further, the results are as shown over here. So next I'm going to show what happens when we have a square-shaped groove. Again, I'm putting this this is not square shaped by any means, just as a representation. We will also look in this case. We haven't looked at it yet. These models take a long time to run on the computer, but the load ranges are seen over here. So I'm just going to go to the final punch. And so this is the low loading creates something like this. And as we increase it, actually, in this case, we seem to be developing more bone as compared to the previous case. So there seems to be some advantages. So these results all need to be analyzed and all need to be compared to histological data, and I look forward to doing those studies. So this is the last slide of my presentation. We used a bone regeneration model to predict bone density variation around a V-groove, a rectangular groove for axisymmetric loading. This showed that both cancellous and cortical bone types can be obtained around both types of grooves. Reduced stresses around the grooves result in less cortical bone quality, like Wolf could have told us about 100 years ago. Some reality checks over here. Model considers only the effect of mechanical loads. Physiological effects, the connection between titanium oxide and bone are only indirectly included in models like this. And we are going to do some more work on the equilibrium value of the strain energy density. We are going to look at different implant grooves. We are going to study a full implant, and we are going to implement a wound healing model for some technical reasons. So thank you very much for your attention. And thank you.